Hey everyone, let's take a look at number 7 in section 4.5 of Achieve. This is the section on L'Hopital's rule, and so we're evaluating the following limit using L'Hopital's rule. And they're taking the limit here as x approaches negative infinity, natural log of the quantity x to the fourth plus 4 divided by 13x plus 1. So you need to know the behavior of this limit as x goes to negative infinity. In other words, as x gets larger and larger in absolute value, but through all the negative values. So x becomes negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000, and so on. What's this ratio approaching? What is that limit? Just to remind us, I just graphed some of the pieces, if you will, of this function. 13x plus 1, if I graph that, that's a line of slope 13, so very steep slope, right? 13. Go over 1, go up 13, and the y-intercept is 1. I also graphed inside here x to the fourth plus 4. It's almost like a parabola. It opens upward. It's not actually a parabola, but it's shifted 4 units up and looks something like this. And then the natural log of just x, I want to just take a look at the natural log of x. There's the graph of that for your reminder. Remember, natural log of 1 is 0. We have a vertical asymptote at x equals 0 as we approach 0 from the positive side. The natural log is going to minus infinity. But as x goes to positive infinity, then we're going to infinity. Now, all that being said, we're approaching negative infinity. Some of you might say, uh-oh, with a natural log function, we can't approach negative infinity, but we're going to be okay. Let's actually look at the bottom first. What's happening to 13x plus 1 as x goes to negative infinity. So as x gets more negative, where are we going on this graph? We're going down this way, right? We're going down to negative infinity very rapidly, right? In other words, as x gets more and more negative, 13x plus 1, even though I'm doing plus 1, this 13 times a negative number is a big negative number, right? And it just gets bigger and bigger. And so this overall is going to minus infinity. Okay, the denominator is clearly going to minus infinity. And then as x goes to negative infinity, well, first of all, we can bring the limit inside the natural log. X to the fourth plus 4, what's happening to that? Well, we can see it from the graph. As x goes to minus infinity, where are we going? Up, 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 going to positive infinity. And that's because you're raising something to the fourth power. So even though these are negative numbers we're plugging in here, they're being raised to the fourth power, which makes the expression positive, right? So positive, and as x gets more and more negative, x to the fourth is getting more and more positive, and x to the fourth plus 4, of course, is going to infinity. So x to the fourth plus 4, as x goes to negative infinity, is going to positive infinity, which means the input to the natural log function, the input, which in this case would be the x value here, the input is getting bigger, so the natural log, notice, is getting bigger. So as x goes to a negative infinity, the natural log of the quantity x to the fourth plus 4 is going to positive infinity. So this limit is of the form infinity over minus infinity, or just infinity over infinity. It doesn't matter, plus or minus. That is an important form because that's L'Hopital rule form, one of them, right? Either 0 over 0 or infinity over infinity. So it's only in those forms can we use L'Hopital's rule. And so L'Hopital's rule, when I use it, I usually put a L over the equal sign. So I'm applying it here, which says the limit of the ratio of these two functions equals the limit of the derivative of those two functions, the ratio of the derivative of those two functions. So I have to take the derivative of the natural log of x to the fourth plus 4, do that on top, and the derivative of 13x plus 1. Well, let's do the bottom first. What's the derivative of 13x plus 1? Pretty easy. That's just 13, right? Derivative of 13x is 13, derivative of 1 is 0. So I just get 13 down here. Up top, I've got to take the derivative natural log of this quantity. Notice this is a composition of functions. We've got inner function x to the fourth plus 4, outer function natural log of u. So it's chain rule, right? We take the derivative with respect to x, natural log of u. It's the derivative of the outer function. The derivative of natural log is 1 over u in this case, right? Times the derivative of the inner function u, which is du dx or u prime. So it's actually u prime over u, right? And so what is u prime? What's the derivative of x to the fourth plus 4? Well, that's 4x cubed. Derivative of 4 is 0. So it's 4x cubed over u, which is x to the fourth plus 4. So this is the derivative, right, with respect to x of the natural log of the x of the quantity x to the fourth plus 4. So the derivative with respect to x of the natural log of x to the fourth plus 4, right, is what we're getting up top here. This is this whole thing here. Okay, and this is the derivative of 13x plus 1. So now this limit of this expression is the same as the limit of this expression, provided this limit exists. So we still got some work to do. Let's simplify, right? Dividing by 13 is the same as multiplying by 1/13. So we'll multiply the numerator by 1/13 and we get this. And now what's happening? Well, as x goes to a negative infinity, we already said x to the fourth plus 4 is going to, again, positive infinity. And so 13 times something going to positive infinity is going to positive infinity. 4x cubed, though, if I look at the graph of 4x cubed, that graph, right, looks like something like anyway this. So as x goes to minus infinity, we're going to minus infinity, right? So x cubed will keep the quantity being negative, right? Plugging in a negative number, but as x gets bigger and bigger in absolute value, 4x cubed just blows up as well. So I get negative infinity up top over infinity. Basically, affinity over infinity again. Does that mean we messed up because we haven't gotten anywhere? No, it just means let's try L'Hopital's rule again. It's still L'Hopital's rule form. So sometimes we have to use it twice, and that's what I'm going to do here. So now I take the derivative of the top function, which is easy. Bring the 3 down. 3 times 4 is 12. Subtract 1 from the exponent. So just the power rule there. And then the derivative here, 13 is a constant multiple. Derivative of x to the fourth is 4x cubed. Derivative of 4 is 0. 4x cubed times 13 is 52x cubed. Okay. Now, you might say, oh, if I plug in, this is going to infinity, this is going to minus infinity, and we're still L'Hopital rule form. Well, wait a minute. You can simplify this first. Notice 12 and 52 have a common factor of 4. 12 divided by 4 is 3. 52 divided by 4 is 13. So 12 50-seconds is 3/13. And what's x squared divided by x cubed? Well, I can divide top and bottom by x squared, and I'm left with 1x down here, right? So I just have 3 over 13x. Well, what's happening as x goes to minus infinity? The top is going where? 3. It's not changing. It's a constant. The bottom, 13x, that's going to minus infinity, right? That's back to, basically this is the same graph, just shifted 1 unit down. But as x goes to minus infinity, we're still going to minus infinity. And what's that? Is that indeterminate? Is that L'Hopital rule form? No, this is determinate. 3 divided by a number that's larger and larger in absolute value, even though it's negative, this ratio is getting closer to 0. It's always a negative number, but it's getting closer and closer to 0. And therefore, we say the limit is indeed 0. And that's the answer. That's the limit of the original expression. If we go all the way back up to here, right, follow all our equal signs, right, that's the limit using L'Hopital's rule. Keep in mind, you can confirm, there's a lot going on here. If you want to check, you can check numerically by simply taking this original function here and plug in what? In this case, values of x that are bigger and bigger in absolute value, but negative. So I would plug in like negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000, and see what's happening. Is it getting closer and closer to 0? Okay. Hope this helps on this one.